Hello, this is a new video from the series Verge3D for Blender Basics. In this part of the tutorial, we'll be thoroughly optimizing our application. To get an idea of how efficient your app is, you can use the puzzles. Go to the System category and drag out the puzzle called Print Performance Info. Now if you open the browser console with F12 and then refresh the app page, it will output some helpful data about application structure. How fast loads the scene, what is FPS, how many triangles are there, how many shaders are used, how many textures, and so on. So let's begin our optimization efforts. The first thing we want to do is to decrease the number of unique shaders and textures. Let's open up the application folder. As you can see, all the images are in PNG format. It is possible to resave at least some of them to JPEG format to save the file size and speed up the loading. Moreover, some of the textures are black and white, and thus we can pack them into the channels of a single texture. It might free some video memory and further speed up the loading. We'll be using the open source image editor GIMP, but of course you can use any other tool such as Adobe Photoshop. Okay, let's start with a carbon-based color texture and resave it as JPEG. Make the compression ratio 93, which is a good trade-off between the file size and quality. Let's do this with a plastic-based color texture as well. For consistency reasons, we'll be also renaming the files at the same time. Let's rename this one as plastic-based-color.jpg. Also resave and rename the wood texture. So, if we check the size, we can see that the JPEG file size is just 250 kilobytes, while the original PNG is almost 1.3 megabytes. So saving as JPEG is a very effective way to drastically improve the loading time for your app. Let's delete the PNG files even if this causes our app to break. But don't worry, as we are going to fix this a bit later. Now let's find out how we can join black and white textures together. We can pack these textures to the channels as recommended by the GLTF format specification. So let's do it with the textures of the carbon material. Open both the roughness and metallic textures in GIMP. Let's put them in a layer each. Make sure we have grayscale mode enabled. This reveals the feature called Compose. This function basically packs image layers into RGB channels. The red channel is intended for an occlusion map. But we have a shared occlusion texture rather than an individual map for each material. So we leave it empty. The green channel, according to the GLTF recommendation, should be reserved for the roughness texture information. Finally, the blue channel should be reserved for the metallic texture. Click OK to obtain a single texture, which we can save. Let's name it accordingly. carbon, Occlusion-Roughness-Metallic.jpg. Again, we'll be using the JPEG format with compression ratio set to 93. Let's see how it is compared with the original images. It was 10 KB and another 10 KB, while the packet texture is 20 KB. This seems to be not a big deal. However, one texture instead of two means saving a big chunk of video memory, which is crucial for mobile devices where memory is scarce. Let's also take a look at the normal map. We won't be saving it as JPEG since it would introduce bad-looking artifacts to the surface. However, it is important to check if there is an alpha channel in this image, because it would make the image unreasonably bigger. So if you happen to have an unused alpha channel in your image, you should definitely remove it. Let's proceed with packing the added textures. Okay, there is only one roughness texture in the wood material, no metallic. Nevertheless, we will create an Occlusion-Roughness-Metallic texture anyway, because we want all the materials to have similarly structured textures for further optimizations, which we'll talk about a bit later. Just leave the red and blue channels empty and fill the green channel with the roughness component, as usual. Save this image as JPEG and rename it as we did with the other textures. Finally, let's delete the original images. At first glance, it looks like a reverse of optimization, since this texture wastes two channels. However, this will help us leverage another optimization method, as we'll see very soon. We are done with the textures. Let's just rename some of the textures, making their names shorter and consistent. So we have carbon base color, plastic base color, and wood base color. Same with normal mass: carbon normal, plastic normal, and wood normal, and so on. So we are finished here. We no longer need GIMP or textures. Let's get back to Blender to proceed. Switch to the shading workspace. Now let's look closer at the materials. If we check out our swatches, we might notice that all three materials basically have the same structure. The only difference is that they have different textures, and also that one of our materials lacks a texture. So here comes another way of optimization. It appears that we can reuse the same shader for all three materials. As such, we can replace textures rather than materials in our configurator. So let's remove the swatches as we no longer need them. We'll be replacing the textures inside just one material, so we can rename it simply as cover. Let's also rename the texture nodes, because we'll be using these names later in puzzles. These two textures we should remove altogether, because they packet the roughness and metallic textures into a single image. So let's load it. In order to use this joined texture, we should add another node, separate RGB. There is nothing in the red channel, because the occlusion texture goes here. This is a special case as occlusion is shared by all the materials. The green channel contains roughness data, so we should connect it with the roughness input. Finally, the blue channel should go to the metallic input of the principal BSDF node. Make sure to set the color space to non-color. Let's also rename this texture to Occlusion-Roughness-Metallic for the sake of clearness. We'll leave this normal map as is, just rename it. Now let's save and open this Blender file several times to get rid of unused images. Here we can see that they are about to be deleted. Do it once again, now they are gone. Now we only have 3 textures for the single cover material and the shared ambient occlusion map. Some image files are missing because we renamed them. So let's fix this. Go to the Image tab of the image editor and open the files again, one by one. Let's open our plastic base color image. The same should be done with the normal map, which we also renamed. Let's check the material. Everything looks alright. Now we can export our scene and check our app again. The material and textures are all here, which is great. However, the configurator buttons no longer work since we deleted the swatches. Let's fix this by modifying this group of puzzles responsible for swapping materials. Remove all assigned material puzzles. We'll be updating a single material instead. We'll be doing it through a puzzle called Replace Texture. Let's place it here. Now we need a material selector, in which we select the material that we name it Cover. This material provides a few texture slots, just like we named them in Blender. Let's select Base Color to replace it with a new texture. To make no mistake, let's go to the application folder and copy the exact name of the image. For the carbon material, it will be Carbon Base Color. Let's paste it in the puzzle and make it JPEG instead of PNG. We can just duplicate this puzzle and modify for Occlusion-Roughness-Metallic texture. Also copy its name and paste it to the puzzle. Finally, let's replace the normal map. This time, the image comes in PNG format. Click on the configuration icon of the Replace Texture puzzle. This puzzle has an optional slot called Once Ready, which is triggered right after a new texture is loaded and replaced. So we can move our variable switch to this slot and thus get rid of the timer puzzle. We'll be doing this after the normal map is loaded, because it is the heaviest of all textures and is likely to be loaded last. Let's save and see how it works in the app. The Carbon button works again, although now it replaces textures rather than materials. This was possible because we placed the texture data in the same channels of the Occlusion-Roughness-Metallic texture and used a unified shader for all material variations. As a result, the textures are mutually replaceable, making the configurator work like a charm. Let's do it for the rest of the configurator buttons. Okay, let's check the final result. Wood is assigned, so is plastic, and so is carbon. Excellent. On the next stage of our optimization efforts, we'll reduce the number of what is known as render calls. To reduce the number of render calls, we can join all objects that use the same shader. The thing is that each separate object requires extra processing to render it. Of course, you won't join objects that are animated or supposed to behave as separate somehow in the app. But if you can have static objects and they share the same material, it helps a lot if you merge them. So let's do it. First of all, let's select both covers and use Ctrl-J to join them. It is now just one object, so we can rename it to simply cover and hide it for now. Next, we have aluminum plates between the instruments. We can merge them into a single object too. We can use the operator select linked, material to select all the parts made of aluminum. Then just use Ctrl-J to obtain a single object. Let's name it plates. Now comes a bit more difficult task. We have lots of objects made of chrome-plated steel. Some of them are animated and others are static, so we'll be merging only static objects. To do this, we hide all the animated objects that made of chrome as well as other parts that are not made of chrome. Use shortcut Shift-L to select objects by material. The only thing we are not going to merge is this small ring, as we'll be using it for some interactivity in one of the future tutorials. Finally, join the selected objects into one, naming it as limiters. Next, there are some parts made of brass. Let's join them as well. The only brass object with paired joining is this small pivot that is animated together with the scissors. So we join them and name the resulting object as rods. Okay, this is it with the scene optimization. We reduced the number of textures, shaders, and render calls. Let's export to Verge3D. Get back to the app, open the browser console with F12, and reload the app. From the performance data, we can see that the scene is now loaded faster. The number of render calls is halved as it was reduced from 18 to something between 9 and 10. This is the result of using less shaders and joining static meshes together. Also, in the section Materials and Shaders, you can see the renewed list of materials. They are so ordered that the heaviest shaders are shown on the top, so that you can focus your efforts on optimizing them first, and dealing with others later, or not dealing at all. The heaviest shader appears to be cover. This is because this material is more complex, with lots of textures, including a normal map. Other materials are much simpler. They only have an ambient occlusion texture. Then come some system shaders, which we cannot influence directly. We can also see here that the app now loads less textures, which is a very good thing. The last but not least thing we should do is enable LZMA compression for the scene files. This helps a lot to speed up the loading time, and is considered as a must-have thing for any web-based 3D application. It works best when we have a lot of geometry in your scene. To enable creating compressed assets, turn on the checkbox Enable LZMA compression in Verge3D settings. Export the scene as usual. It will export a bit slower from now on, but for such a small project, it is not that noticeable. So now we have assets in the compressed form. However, we should also enable loading of these compressed assets in the app. To do this, switch to the Init tab and drag out the puzzle called Configure Application. In this puzzle, check Compressed Assets. This will make our app load compressed scenes rather than uncompressed. The latter are still available in the application folder. The loading time might not be improved much because we are checking this app from the local system. However, after you deploy your app on a web server, the loading time will become crucial for user experience. There is one last thing we want to do. It won't affect this particular application because we don't use any lights. But just in case, let's disable shadows for this scene. Real-time shadows is a very heavy technique, so if you are not going to use them in your app, it is better to turn them off altogether to free the engine resources. Okay, let's do the final export in this video. We can now delete the performance info puzzle as we no longer need it. This is it. Thanks for watching and see you in the next video.